Okay, I hope I'm audible to all students who are attending this lecture of Mathematics Class 12. We continue with our lectures on linear programming. And if all students can recall that in the previous lecture of linear programming, we were looking at the linear programming problem. We had done theory in the last lecture. We had looked at what is meant by a linear programming problem, what is meant by an objective function, what is meant by a constraint, what is meant by an optimization problem. We had also looked at the concept of feasible region and feasible solutions in the previous lecture. Okay, and in the previous lecture, we also had done two important theorems. Okay, now in this particular lecture, we intend to look at the corner point method to solving linear programming problems. So our heading now is corner point method, the corner point method to solve linear programming problems. Okay, so let's look at this particular method. In today's lecture, we are also going to do some numericals. Okay, so let's write the corner point method using steps. Okay, so we have step one. Step one, find the feasible region of the linear programming problem. Find the feasible region of the linear programming problem and determine its corner points. Determine its corner points. The corner points are also called vertices, either by inspection or by solving the two equations of the lines intersecting at that point. So guys, this is our step one. Okay, first of all, we are going to solve for the feasible region. Now, from the last lecture, all of you can recall, how do we find the feasible region? We solve all the inequalities simultaneously. That means we do the shading. Okay, we are given the inequalities, we are going to shade the required area, and the common shaded area after plotting all the inequalities is going to give us the feasible region. Once we get the feasible region, we are going to locate the corner points, also called the vertices, either by using inspection, by looking at the graph, or we are going to solve the two equations of the line intersecting at that point. Remember, at the vertex, when I say at the vertices, at a given vertex, two lines are going to intersect. So one method of finding the coordinates of the vertex is by inspection. You just look at the graph and you get the coordinates of the vertex. Another method of solving for the coordinates of the vertex is that whatever two lines are intersecting, you solve both of them simultaneously. That is going to give you the coordinates of the vertex in the Cartesian graph. Okay, so this was step one. Step two. Evaluate the objective function. Which is z equal to ax plus by at each corner point. Now all students can recall from the previous lecture that z equal to ax plus by was my linear objective function. And we are going to evaluate the objective function at all the corner points I have found in step one. In step one, I found all the corner points by plotting the feasible region. In step two, I am going to put all those corner points in my objective function. I can say let capital M and small m respectively denote Let capital M and small m respectively denote the largest and the smallest value of these points. The largest and the smallest values of these points. So capital M denotes the largest value which Z takes. Small m denotes the smallest value of these points. Okay, that means capital M will be the highest value of Z I can get, and small m will be the lowest value of Z we can get from the points in the feasible region. Okay, now within this, so now I can move on to step 3. Let's look at step 3. Within step 3, point A, when the feasible region is bounded, when the feasible region is bounded, then capital M and small m are the maximum and the minimum values of Z. They are the maximum and the minimum values of Z. Okay, remember we had done the concept of boundedness in the last lecture. Okay, a feasible region is said to be bounded if it can be enclosed within a sufficiently large circle. We had done this in the previous lecture. Any feasible region, I repeat, is said to be bounded if you can enclose that feasible region within a sufficiently large circle. However, that feasible region is said to be unbounded if that feasible region cannot be put within a circle. It means it's going to extend infinitely in any given direction. So when your feasible region is bounded, then your capital M is the maximum value of Z, your small m is the minimum value of Z. Okay, and then we have point B. If the feasible region, if the feasible region is unbounded, if the feasible region is unbounded, we go to step 4. If the feasible region is unbounded, we then go to step 4. Now I am writing step 4 for all students on the top of the screen. Okay, so on the top of the screen, let's look at step 4. Step 4 we'll go to only when our feasible region is unbounded. So within step 4, point A, M is the maximum value of Z. M is the maximum value of Z if the open half plane, determined by, how do I find the open half plane, guys? Ax plus by greater than M, has no point in common. The open half plane has no point in common with the feasible region. Okay, if it has a point in common with the feasible region, I can write otherwise. Z has no maximum value. So guys, when my feasible region is unbounded, I am going to go to step 4. Within step 4, I will call capital M as the maximum value of the function Z, objective function Z, only if the open half plane determined by Ax plus by greater than M has no point in common with the feasible region. But if it has a point in common with the feasible region, then Z is not going to have the maximum value. Similarly, I can write within step 4, I am erasing step 1 now, and within step 4, I can write the second point, which is for minimum value. Okay, so erasing this off, let's look at the second point within step 4. So point B is as follows. M is the minimum value of Z M is the minimum value of Z if the open half plane, determined by ax plus by less than m, less than small m, let me correct myself, ax plus by less than small m has no point in common, with the feasible region. Okay, and I can say if it has a point in common with the feasible region, which means otherwise I can say that Z has no minimum value. Otherwise, Z has no minimum value. So hoping all students have understood this, I can quickly revise the corner point method again for solving for linear programming problems. Step 1, you are going to find the feasible region of the linear programming problem. How do you find the feasible region? You plot all the inequalities given to you, check out for the directions. The common shaded area you will be getting will be called the feasible region. Okay, and once you have found the feasible region, you are going to find the corner points or the vertices of that feasible region either by inspection or by solving the equations of the lines who are intersecting at that vertex. Step number 2, in the objective function, you are going to put all the corner points you calculated in step 1. The largest value of Z will be called capital M. The smallest value of Z will be called small m. And step 3, when your feasible region is bounded, if it can be enclosed within a circle, sufficiently large circle, capital M is the maximum value, small m is the minimum value. If your feasible region is unbounded, cannot be enclosed in a circle, in that particular case, capital M will be called the maximum value only if the open half plane determined by this particular inequality has no point in common with the feasible region. If it has a point in common with the feasible region, then Z has no maximum value. On the other hand, small m is the minimum value of the objective function Z if the open half plane determined by ax plus by less than m has no point in common with the feasible region. If it has a point in common with the feasible region, then Z has no minimum value. So these are the 4 steps for calculating for solving the linear programming problem by the corner point method. Now, guys, let us practice some questions based on this particular concept. So, practice questions based on solving the LP, or I can say the linear programming problem by corner point method. By the corner point method. So let us look at the practice question based on this. So question 1. Solve the following linear programming problem, LPP, linear programming problem graphically. Okay, so we are given maximize Z equal to 4x plus y subject to following inequalities: x plus y less than equal to 50, 3x plus y less than equal to 90, x greater than equal to 0, y greater than equal to 0. Okay, so guys, first of all, you can clearly see that this is my objective function and these are all my inequalities, or I can say my constraints. Okay, now let's quickly solve this problem. First, we are going to plot all the inequalities. So to plot, first of all, let's consider them as the equality x plus y equal to 50. When x is 0, y is 50. When y is 0, x is 50. Okay, then let's plot 3x plus y equal to 90. First, we plot them at the equality. So when x is 0, y is 90. When y is 0, x is 30. Okay, so now we are going to plot them in the graph. So let's quickly look at the graph now. So I am drawing the graph on the right hand side. Okay. We have the x-axis and we have the y-axis. The scale I can take is of 10. So suppose I take the scale as 10. So, or I can even take the scale as 20 because of lack of space. So 20, 40, 60, 80, 100. And on the x-axis, I can take the scale of, again, I can take 20, 40, 60, 80, 100. We only need the first quadrant, by the way, because of the non-negativity constraint. X and y should be non-negative, so we only work in the first quadrant. Now let's plot this, guys. When x is 0, y is 50. When y is 0, x is 50. So this is my one constraint. This is x plus y equal to 50. Now, guys, I have to plot x plus y less than equal to 50. So where will the shading happen? Put x as 0, put y as 0. So 0 plus 0 is equal to 0. Is 0 less than equal to 50? Yes. So shading will be towards the origin. Shading will be towards the origin. Very simple. That means my shading will be in this area, towards the origin. And the equation of the line is nothing but x plus y equal to 50. X plus y less than equal to 50. How did we shade the area? I'm repeating again. Put x as 0, y as 0. 0 plus 0 is 0. Is 0 less than 50? Yes. Shading will be towards 0. Then similarly, guys, we can quickly solve for 3x plus y less than equal to 90. So I'm using red color now. So first it's going to be x as 0 and y as 90. So x is 0, y is 90. Y is 0, x is 30. Y is 0, x is 30. Okay. So I plot this now. This is the inequality I get. Okay. And now where will the shading happen, guys? So if you look at it, 3x plus y is less than equal to 90. Put x and y both as 0. So 0 is less than equal to 90, true. So shading towards the origin. Since 0 is less than equal to 90, it's satisfying the inequality. Shading is towards the origin. So guys, the shading will be towards the origin. Now look at that particular portion where you have black shade and red shade both. So if you look at that region, guys, it's nothing but this region. Now in brown color, you can see the required region. I am darkening it in brown color for all students. This is my feasible region. The brown shaded region is my feasible region. Okay, so this is how we have found it. It's this particular part, and everything to the left of it. Now, how do we find the corner points, guys? This is one corner point, which is 0, 50. This is another corner point, which is 0, which is 30, 0. And then, guys, we have this point also, the point of intersection. Now, how do I find the point of intersection? You solve this equation and this equation simultaneously. You're going to get the point of intersection. We know how to solve two equations simultaneously using the method of elimination. Okay, so x plus y equal to 50, 3x plus y equal to 90. Automatically, you can see y is going to get eliminated when I subtract them. When you subtract them, what do you get? X minus 3x is minus 2x, 50 minus 90 is minus 40. That makes it x as 20. When x is 20, y is 30. So clearly you can see this is nothing but 20, 30. So we have got all the required points now. And there is one more corner point 0, 0, where both the axes intersect each other. This is another corner point 0, 0, the origin. Okay, but one point I want to make clarify, guys, we are not going in the negative axis. So since x and y both should be greater than or equal to 0, we are not going in the negative axis. So ideally our region will be what? Our region will only be this. Let me correct myself. This will be only my required region. So if I erase all the shaded areas now so that students don't get confused, I can just show this by arrows now. You can clearly see when in case of the black line, the shading was here. In case of the red line, the shading was here. If you combine them, your feasible region is only this. This is the feasible region we get when we take into account the fact that x and y should both be greater than or equal to 0. So this region, this and this is my required feasible region. And we have another corner point 0, 0. So I can write this is nothing but my feasible region. Now all students can see that this feasible region is bounded. I can enclose this region within a large circle. It lies within the circle. Since it's bounded, we can quickly find the maximum and the minimum. Very simple. Okay, so I erase this off now and I can write the following. I can write the following, that since the feasible region is bounded, since the feasible region is bounded, therefore we can use the corner point method to find the maximum value of z. We can use the corner point method to find the maximum value of z. Now, how do we find the maximum value of z? I erase the initial part. Just put the points we have got in the objective function. So I can make a table now. I can make this table. We have z, which is nothing but 4x plus y. And then we have the points. Whatever points we got. So I can write my corner points. So guys, when my corner point is 0, 0, what is the value of z? 0. 4 into 0 plus 0. When my corner point is 0, 50, what is the value of z? 50. Because 4 into 0 plus 50 is 50. When my corner point is 20, 30, the value of z is 4 into 20 plus 30, which is 110. And similarly, I can write when my corner point, or let me take the corner point here only. Let me erase this off now. When my corner point is 30, 0, my value of z is how much? 4 into 30 plus 0, which is 120. So at these 4 corner points, the values taken by z are 0, 50, 110, 120. What is the maximum value? 120. So clearly I can say that this is my maximum. So I can say therefore z attains the maximum value equal to 120 at 30, 0. This is the final answer for this question. So hoping all students have understood this. Let's practice another question. Question 2. Okay. Solve the following linear programming problem graphically. Solve the following linear programming problem graphically. Objective is minimize z equal to 200x plus 500y subject to the following constraints: x plus 2y greater than equal to 10, 3x plus 4y less than equal to 24, x greater than equal to 0, y greater than equal to 0. Again, guys, how are we going to solve this question? Very simple. First of all, we are going to plot the inequalities. Okay. So x plus 2y equal to 10. If I plot it, then x is 0, y is 5, and y is 0, x is 10. Then I can plot 3x plus 4y equal to 24. When x is 0, y is 6. When y is 0, x is 8. Now I can plot them in the graph. So I am drawing the graph on the right hand side. Okay. Again, I am not drawing the big graph because ultimately we need the first quadrant only. We need the first quadrant only. So I am just drawing the first quadrant. Okay. This is x-axis. This is y-axis. Okay. X goes on till 10. Maximum is 10, and y goes on maximum till 6. So I can write 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this is with 1 centimeter gap. They are all equidistant. Okay, with 1 centimeter gap. Okay. I can further go forward. And now we can quickly plot when x is 0, y is 5. When x is 0, y is 5. And when x is 10, y is 0. So this is my first inequality. This is my first equation. Equation of this line is x plus 2y equal to 10. Now guys, where will I shade? So consider x plus 2y greater than equal to 10. Put x and y both as 0. So 0 plus 2 into 0 greater than equal to 10 is 0 greater than equal to 10, not possible. And 0 be greater than 10, not possible. So shading away from the origin. That means, guys, shading will be not towards the origin. It's going to be away from the origin. Shading will be in this direction. But let me erase this because we only deal with the first quadrant. So shading is always in the first quadrant here. So it's going to be shading in this direction. And then I can look at the shading for the other inequality. Similarly, I can say consider 3x plus 4y less than equal to 24. Again, if I put both x and y as 0, is 0 less than equal to 24? Yes. So shading towards the origin. So guys, first of all, let's plot in red color the inequality when x is 0, y is 6. When x is 0, y is 6. When x is 8, y is 0. So let's quickly join this. This is our red line. The equation of the red line is nothing but 3x plus 4y equal to 24. And you can clearly see the shading in this case is towards the origin. It is towards the origin. Okay, so guys, you can clearly see when you combine the black and the red color, the black color was this, and the red color is moving in the opposite direction. The common shaded area you can see is this in brown color. This is going to be my common shaded area, which is nothing but my feasible region. And you can clearly see, guys, the feasible region is bounded because you can enclose this within a large circle. Okay, so I can write this. First of all, I can find all the corner points. This is 0, 5, the first corner point. This is 0, 6, another corner point. And I can find this, guys. What will this be? I can solve both the equations simultaneously, which is going to give me the point of intersection. Okay, so erasing this particular part off, let's quickly find the point of intersection. Okay, so x plus 2y equal to 10, 3x plus 4y equal to 24. I can use method of elimination, multiply by 3, multiply by 1. So this becomes 3x plus 6y equal to 30. 3x plus 4y equal to 24. Subtract them. So this implies 2y is equal to 6, which implies y is equal to 3. This was equation 1. Equation 2, equation 1 minus 2 implies equation 1 minus equation 2 implies 2y is equal to 6, which implies y is 3. When y is 3, what will x be? Put it here. X plus 2 into 3 is equal to 10, which implies x is 10 minus 6, which is 4. So this point is 4, 3. So we have got the 3 corner points, and I can write, since the feasible region is bounded, we can use the corner point method. We can use the corner point method to find the minimum value of z. And how will we find the minimum value? I erase this particular part now. Quickly, we can work out the minimum value of z. Okay, so we have the corner point. Let me write the corner points first, and then I am writing the value of z, which is 200x plus 500y. Okay, so my first corner point is 0, 5, then I have 0, 6, then I have 4, 3. Put 0, 5 in the objective function. It's 200 into 0 plus 500 into 5, which is 2500. Put 0, 6 in the function. 200 into 0 plus 500 into 6, which is 3000. Put 4, 3 in the function. 200 into 4 plus 500 into 3, which is 800 plus 1500, which is 2300. So clearly, guys, you can see objective was to minimize. So what is the minimum value of z? Between 2500, 3000 and 2300, you can clearly see your minimum value is this. So I can say this, the last value is nothing but my minimum value. This is my, so I can say therefore z has the minimum value equal to 2300 at the point 4, 3. This is the final answer for this question. So hoping all students have understood this question. So students, this is where I intend to stop in this particular lecture. The objective was to discuss with all students how to solve the linear programming problems using the corner point method. Okay, now homework for all students who are attending this lecture. Exercise 12.1 of NCERT. For all students who are attending this lecture, please start solving exercise 12.1 of NCERT. Okay, I am writing all questions which the students are requested to solve. Question 1, 2, 3, 4, 5, and 6. Homework for all students who are attending this lecture. Please take this homework as homework. Exercise 12.1 of NCERT, questions 1, 2, 3, 4, 5, and 6. So I stop at this particular lecture. I hope all students have enjoyed this lecture. Any doubt, you can unmute your mic and ask, or call up or mail me your doubts at divineschoolofelconomics@gmail.com. So this is where I stop in this lecture.